Welcome to this session on drilling optimization, Total ROP, enhancing techniques and technologies, submodule 4 of 4. In this session, we'll focus on how modern monitoring techniques, automation, and digital systems can improve drilling efficiency, safety, and reliability. Let's begin by looking at the objectives for this module. In this submodule, our objectives are straightforward but critical. First, we'll examine the role of rig systems monitoring and automation, focusing on how advanced networks capture and process real-time data. Second, we'll discuss the health of drilling tools and the predictive measures that help us prevent failures before they occur. Third, we'll explore how measurements and interactions across the rig are integrated from surface to downhole systems to support automated responses. Fourth, we'll highlight the importance of rig safety, particularly how sensors and automation reduce human exposure to high-risk activities. Finally, we'll connect these concepts to emerging applications such as autonomous directional drilling and advanced downhole automation, showing how they contribute to improved wellbore quality and reduced operational time. By the end of this session, you'll have a clear understanding of how monitoring underpins safe and efficient drilling. Rig systems monitoring and automation form the backbone of today's drilling optimization. At the most basic level, we move from simple rig networks to intermediate and highly advanced distributed control networks, capable of handling tens of thousands of input and output points. These networks collect data from a wide range of drilling sensors, both surface and subsurface. The information is stored, processed, and shared across systems that track equipment usage, rig operations, and even energy consumption. For example, monitoring ton miles and rotation hours helps us anticipate mechanical wear, while tracking diesel use and lubrication schedules ensures optimal efficiency and maintenance planning. This graphic illustrates the evolution of rig data networks. On the left, we see a simple rig network with around 1,000 input and output points. At this stage, monitoring is limited to basic surface parameters and a narrow set of equipment signals. As networks expanded, we entered the intermediate stage, shown in the central circle, where rigs developed drilling control and data storage networks, often referred to as DCNs. This was the onset of integrated rig intelligence, capturing information from both surface and downhole sensors and storing it in real time for analysis. Moving to the right, we see today's advanced networks capable of handling between 25 to 30,000 I/O points. At this scale, rigs act as digital ecosystems, integrating predictive maintenance, automation, and remote operations. This growth in connectivity underpins modern drilling efficiency and safety. One of the most valuable benefits of rig monitoring systems is the ability to track the health of drilling tools in real time. By measuring key parameters such as wear, vibration, operating hours, and lubrication cycles, we can predict when a tool is nearing failure. This allows us to intervene early, avoiding costly downtime and unplanned events. Examples of the type of digital information that can be stored and monitored include drilling surface and subsurface sensors, rig maintenance schedules, ton miles, rotation hours, diesel consumption, and lubrication schedules. It also covers all rig tools, rig operations processes, and the integration of wear sensors. Taken together, these create a complete picture of equipment health. Next, we'll build on this idea by looking at how systems measure and interact across the rig to drive automation. Rig intelligence is built on the Internet of Things, or IoT. This diagram highlights the main contributions that make the Internet of Things effective in drilling operations. At the core is communication between things. Devices such as sensors, actuators, and robots are connected to a network, sharing information in real time. This enables systems to coordinate, synchronize processes, and pass instructions from one function to the next. The next element is autonomy. Connected devices are capable of executing programmed tasks independently. They can read incoming information, perform an action such as adjusting pump flow or stopping tripping, and then transmit the result to the next system in the workflow. Artificial intelligence builds on this by applying algorithms to data streams, detecting patterns, and producing new knowledge. This is where automation transitions from following instructions to learning and optimizing. Then we have intelligent. This means the system can learn from experience by applying data-driven and machine learning algorithms. Over time, it improves its decision-making capability. Separate from this is the concept of the thing. A thing is any physical element, like a robot, sensor, or actuator, that is equipped with electronic capabilities and connected to the network. Finally, processing power enables all of these functions, handling the huge data volumes needed for real-time rig automation. Here, we see how intelligent devices, each with embedded microchips, communicate across the rig network. These things can learn from data, execute programmed tasks, and synchronize with other devices to manage processes from start to finish. The concept is decentralized. Each device is autonomous but connected, enabling the system to act in a coordinated way. Machine learning algorithms process the incoming data, generate new insights, and issue instructions to robotic systems or control loops. This integration of IoT sets the foundation for more advanced rig monitoring, which we examine next. Now let's look at measurements and interactions, which form the backbone of rig automation. Starting on the left, the first box shows that the system measures all variables to detect and control machine sequences. This includes block position, pump strokes, and top drive status, ensuring every step in the drilling process is sequenced correctly. The second box shows how data is measured in context, integrating drilling services. In this example, managed pressure drilling parameters are displayed, showing how surface and downhole data combine to maintain safe and efficient operations. The third box describes drilling automation. Here, systems measure references such as weight on bit or torque, then automatically adjust rig elements to optimize rate of penetration and maintain stability. Finally, the fourth box shows conditional monitoring. If values deviate, for example, an unexpected trip tank volume, the system halts tripping and checks flow before resuming, preventing escalation. Together, these interactions enable safe, optimized, and automated drilling workflows. Overall, the rig becomes an intelligent decision-making environment where actions are triggered in real time based on operational conditions. This connects directly to safety, which we'll review in the next slide. Safety is one of the strongest drivers of rig automation. The 2018 IADC incident statistics show that 42% of drilling incidents occur on the rig floor and over 23% during tripping operations. By embedding sensors and robotic actuators, we can reduce the need for personnel in these high-risk zones. The log chart on the highlights time versus drilling operations when under control of rig automation. The key point to note is the low variation, where the operation of a connection is delivered safely in exactly the same way every time. Importantly, this allows us to remove roles like the derrickman from direct exposure on the rig, shifting tasks to remote centres where safety is maximised. This enhanced safety foundation enables us to apply automation directly to operational sequences, as shown in the next slide with a video on the one drill rig, which is the SLB automated design. Here we see how intelligence is applied from connection to connection. Automation today delivers a complete suite of integrated functions. Driller stand for automated sequencing, Total ROP for penetration optimization, auto downlink for tool control, auto survey for automated survey management, and smart tripping for safety. Each automated function builds on the next, connecting pre-connection, drilling, and post-connection activities in one workflow. This eliminates gaps where human error might otherwise occur. In practice, this means the driller supervises rather than manually executes repetitive steps. The system manages downlinks, surveys, and even corrective actions in real time, enabling consistent performance across shifts and crews. In the video, we will see an automated connection. On the display on the left is the list of commands in the system. On the right side of the display are the drilling parameters, such as ROP and block position. In the video, the remote center requests to do a downlink to the rotary steerable tool. The display requests for the driller to acknowledge. Later in the simulation, the system identifies shock and vibration and requests to work through a step-by-step process to return to stable drilling. With this understanding, we move on to a video on autonomous directional drilling.
Right, go ahead. Authority is given. Please turn confirm. Oh yeah. Pumps are on. Pumps on. Rotation on. Bottom.
This tool drills holes. This tool drills holes and connects thousands of engineers across the planet and streams live data through a network of satellites orbiting the globe. This tool drills holes and explores hidden worlds miles below vast rolling plains, minimizes its footprint while trekking under remote frontiers, and endures crushing ocean depths. This tool drills holes.
We have signal acquisition and track confirmed.
and measures the exact strength of the Earth's gravitational and magnetic field every second. That helps to characterize and define its exact subsurface location so that a downhole autonomous steering algorithm can determine the precise changes to keep you right on plan. This tool drills holes and tells you where it is and what it's doing and regulates its own energy. It draws maps, performs gyro surveys, and conducts fluid analysis. Yeah, even petrophysical analysis and geology. This tool drills holes and sees through rock like a superhero and warns you when there's something bad. This tool drills holes and stays on track even when heading into the mysterious zone of exclusion. It can even drill all the way to the center of the Earth in a single run. Not really. But this tool does drill holes and helps you sleep at night or spend more time with your family. Because this tool isn't a tool. It's really a key to a gateway created by the people who write the code that drives the hardware that drills the holes autonomously. Introducing autonomous directional drilling. The future of how you drill holes starts here.
Automation ensures smoother and maintains the trajectory in real time. This leads to straighter, smoother wells, reducing friction factors during casing runs and completions. It also means less time is wasted correcting deviations, which directly lowers drilling costs. By addressing dysfunctions at the bit rather than waiting for surface response, downhole automation fundamentally improves drilling economics. Here we illustrate the scope of rig automation hardware. The images show robotic systems like the bridge racker, SmartCat, riser catwalks, pipe deck cranes, and manipulator arms. Each is designed to move heavy tubulars and equipment without direct human involvement. For example, the bridge racker manipulates pipe in 3 dimensions, while the riser catwalk delivers and picks up risers with a 10-ton lifting capacity. The manipulator arm connects mud hoses and replaces them quickly, eliminating manual handling risks. The overall result is faster operations, reduced risk exposure, and more consistent handling of pipe and riser systems. Next, we'll look at a short video on drill ops used on the Peregrino project for Equinor.
We worked together with a customer to do something amazing. The first ever autonomously drilled section using full rig automation and autonomous on-bottom directional drilling. Working together on a razor-thin 1.58 metre centre-to-centre distance, we successfully drilled a 2.6 kilometre section with a 60% increase in ROP, outperforming the plan, all while reducing carbon emissions by 16%. To make things safer, more efficient and cost-effective, we integrated surface and downhole automation combined with our autonomous capabilities that help to minimise human intervention. Now, autonomy and automation are not the same thing. Automation is when equipment follows instructions to carry out repetitive tasks. On the other hand, autonomy involves technology assessing conditions, even unexpected ones, and then making adjustments. When combined, the two elevate efficiency. So how did we do this? We started with a cross-disciplinary team that worked as a united force. Then we used our sequencing software to automate pipe handling connections, as well as trips in and out of the hole. DrillOps, SLB's intelligent well delivery solution, automated on-bottom drilling, while our Neuro autonomous solutions figured out the best steering sequences and parameters to reach the target. Not only did we make operations safer and more consistent, but we also significantly cut carbon emissions while boosting drilling performance. And we've drilled the most autonomous well to date, using full rig automation and autonomous on-bottom directional drilling. And the best part? It was all monitored remotely in real time.
Let's review the objectives we set at the start. First, we aim to understand rig systems, monitoring and automation technologies. We covered how networks capture and process thousands of data points, enabling predictive analysis. Second, we wanted to recognise predictive maintenance for rigs and tools. We explored how data on rotation hours, ton miles, and wear sensors forecast failures before they happen. Third, we sought to learn conditional monitoring and automated responses. We saw examples like stopping tripping operations when the trip tank volume deviates. Fourth, we evaluated rig safety improvements through sensors and remote control. By removing personnel from the rig floor and controlling operations remotely, exposure to hazards is greatly reduced. Finally, we explored automation in directional drilling and downhole operations, from auto ROP and auto survey to autonomous steering and downhole optimization. Together, these objectives show how automation transforms rig operations into safer, smarter, and more consistent systems. That concludes Submodule 4 of 4 on Total ROP Enhancing Techniques and Technologies. Please proceed to the quiz to reinforce today's learning. Thank you for your time and attention, and I look forward to seeing you in the next module.